Hi, I'd like to give a short introduction about scientific notation, especially that's pertinent to our use in chemistry classes. There's a number, a value written down on the board, 3,600. I'm not sure what that number is. It might be number of students that are enrolled at a university. It might be a very rough estimate of somebody's bank account, and so we're not sure exactly how many significant figures are in this. Many sources tell us to ignore the zeros on the right unless that there's a decimal place. So let's go ahead and assume that the 3 and the 6 are significant and that the zeros are placeholders. 3,600 isn't too bad of a manageable number, but we'd like to express this in scientific notation. Scientific notation is used for numbers that are very large or very small, and it allows us to minimize the use of digits, of numbers that we're writing. It also allows us to reflect precisely the number of significant figures. What we do to put this number in the scientific notation, or in a factor of 10, is we go ahead and locate a decimal place after one digit, and so this number will become 3.6. Let me go ahead and write the value 3.6 up on the board. Now I've lost the placeholder zeros, and so 3.6 obviously is not the same value as 3,600, but 3.6 multiplied by a factor can be equal to 3,600. Now that factor here is going to be 1,000. There's a decimal place right here, and it needs to move over once, twice, 3 times in order to be the value 3.6. I'm going to express this in scientific notation by saying that 3.6 is multiplied by the number 1,000. 1,000 is written as 10 times 10 times 10, or 10 to the third. There's no ambiguity with the number of significant figures. I've reduced the actual numbers here to 2, 3.6, and I've expressed this in scientific notation as a base 10 number. Going the opposite way, if somebody had given us a number in scientific notation and we expressed it in standard form, we do the same by evaluating where the exponent goes. For example, if somebody gave us 4.7 times 10 to the second, we might speak that number to somebody right now as saying 4.7 times 10 squared, 4.7 times 100. Now what it's going to tell us is the exponent of 2 will tell us we're going to move the decimal place over twice. I'm going to list this number as 470. I needed to include a 0 here as a placeholder. I am not allowed to go ahead and put a decimal place after this because a decimal place after this would go ahead and presume that that 0 is significant, and we don't know what the value is after the 7, so it remains. Sometimes students would like nice rules, like how do I know which way to move the decimal place? Generally speaking, this number is large, meaning it's larger than the number 1. And so our exponent here of 3 will be a positive value, 3.6 times 1,000. When we started here, we knew that the number was going to be larger than the number 1 because of the positive exponent, 4.7 times 100. Both of these values are larger than 1. Let's take a look at some examples where the number is small, meaning smaller than 1. Somebody provides a value of 0.00270. There are 3 significant figures in this value, the 2, the 7, and the trailing 0. These zeros on the left are simply placeholders. I would like to express this in scientific notation. I'm going to write the value 2.70. The 2, the 7, the 0 are all expressed there. They're all significant, and I include the 0 at the end. The decimal place is here, and 1, 2, 3 transitions are needed to go ahead and have the decimal place after the first number, which is a 2. I'm going to write times 10 to the negative third. 1, 2, 3. I moved the decimal place over 3 times. Perhaps you might think of this as being dividing by 1,000. The value here, negative 3, is negative. That's a reflection that this number is small, speaking of smaller than number 1.